A time series can change rules halfway through. Ruptures finds the breakpoints, so you do not model one regime as if it were another. You'll learn how the pieces fit into a workflow that highlights regime shifts and reports them clearly. I'm Professor Pi, teaching AI foundations with simple Python. Change point detection answers a practical question. When a process shifts, how do you spot when and how much? Teams use it to avoid training one model across mixed regimes, to trigger retraining, or to annotate dashboards so analysts don't misread averages. In monitoring pipelines, it usually runs on rolling windows of a few thousand samples, and you must balance sensitivity against noisy blips. Think of change point detection, like watching a sensor that sits flat, then climbs, then flattens at a new level. A detector finds the boundaries between those plateaus. It's most reliable when shifts change means, variances, or trends, and less reliable when changes are subtle or when the series is strongly autocorrelated. We'll build a small, clear pipeline, step by step. First, we synthesize a controlled 3-regime signal you can inspect. Next, we detect candidate breaks and rank which jump matters most for retraining. Then we enforce a minimum segment length to ignore short blips. Finally, we append new data to validate the monitor. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we synthesize the controlled signal so you can inspect the raw shifts visually. This snippet assembles a deterministic 3-regime signal and measures how sharply its mean shifts. Forecast pipelines fail when a baseline like our first plateau abruptly gives way to a much hotter second regime, because prior loss surfaces assume that calmer variance. The list comprehension building segments keeps the regimes compact while still hinting at gradual trends inside each block. Concatenating them into signal exposes how even smooth intra-segment drift still yields large differences in the aggregated means stored in means. The printed mean shifts figure shows why blindly training across the whole window would smear valuable contrast. Now we need to turn that signal into candidate breakpoints and see what Ruptures reports. This example runs ruptures.Pelt on the shared signal to retrieve candidate breakpoints under an L2 cost. Missing these pivots would leave monitoring dashboards averaging incompatible behavior. So we keep penalty at 8 to balance sensitivity against over-segmentation. The call to ruptures.Pelt binds the data once, and algo predict pen equals penalty lets us dial different penalties without recomputing cost matrices. Filtering out the trailing lens signal entry produces the cleaner detected list of actionable boundary indexes. The printed Pelt breaks report confirms where the algorithm says the regimes reboot under this configuration. With candidate breaks in hand, ask which transition hurts performance most and should trigger a retrain. This code ranks the Pelt-derived regimes to show which transition most disrupts downstream estimates. When you refresh a model, you need to decide which break to anchor retraining on, so we push the cuts list through segment means to quantify each plateau. The list comprehension in mean changes turns consecutive means into absolute gaps, and sorted orders them from most disruptive to least. That ranking runs entirely in memory, making it easy to reuse if new breakpoints arrive from a batch pipeline. The printed largest shift index line spotlights the dominant gap, so you know which regime change deserves first attention. Operational teams often require ignoring very short segments. Next, we enforce a minimum segment size and compare results. This snippet reuses ruptures.Pelt with a strict min size to mimic a service level rule that ignores fleeting blips. Operations teams often reject segments shorter than a maintenance window. so we refit with min size equals 60, before predicting with the same penalty. By reapplying algo logic through wide algo, we let the pruning engine respect the duration constraint instead of bolting on manual filters. Comparing constrained to detected lets us quantify how much structure we sacrifice once the guardrail turns on. The printed min-size breaks line shows the surviving breakpoints and how many signals were dropped relative to the default run. Finally, monitors must recheck segmentation after new data arrives. We simulate that next. This example appends a fresh regime chunk and reruns ruptures.Pelt to confirm the latest shift is surfaced, without revisiting the segmentation after new data lands. A forecasting system might keep extrapolating the stale third regime. The code concatenates new block onto signal, fits monitor algo once, and reuses penalty, so the decision threshold stays consistent with earlier calibration. The generator inside max isolates the newest actionable breakpoint, while break count counts how many regimes the stream now holds. The printed latest start value verifies the monitoring loop would alert you right at the new segment boundary. To map this toy flow to a real system, picture an electricity load monitor. Swap the synthetic signal for recent load samples. Run the same detection steps and trigger model retraining when the largest ranked shift crosses your business threshold. The penalty and min-size calibration from the toy run become a simple alerting policy you can test in staging. 3 quick points to hold on to. Change point detection finds where a time series changes behavior. Use it when regimes would invalidate a single global model or hide actionable shifts in dashboards. And be careful, noisy data and short-lived blips create false alarms unless you tune penalty and min size. A useful next step is to tune the penalty across a small labeled validation window and pick the penalty that balances missed shifts against spurious cuts. Try that calibration on a representative dataset, household power consumption, or a rolling week of your production metric, and measure how often alerts actually match incidents. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.